Okay. So hi, good morning. Go green. Okay, that's fine. You're not natives. You're normally supposed to say go white. My name is Jaideep Taggart Singh. I'm a professor here at the Facility for Rare Isotope Beams, and I also teach in the physics department. And I'm actually an experimentalist. And I'm going to give you I call it an idiosyncratic perspective on what this facility is, but I'm going to try to do it with some perspective in terms of history, so you can get an idea of how some of these things are connected. And I'll sort of come back to this, but one interesting thing about nuclear physics in Michigan State is that before 1959, it was non-existent. There was not a single nuclear physics person here. And the president of the university at the time decided that MSU needed nuclear physics. And so a committee was set up to do a study to see what kind of, how to bring nuclear physics here. And it was decided to build a cyclotron on campus. And so they hired a guy named Henry Blosser, who was an expert at building cyclotrons. And he was at Oak Ridge at the time, pretty young man. And they brought him on board, and he hired two other people to help him build the first cyclotron here. The first person was a guy named Morton Gordon. He was a theoretical physicist, and he was completely blind. And he actually taught classes writing on the chalkboard with perfect handwriting, with perfect clarity. And in fact, he even wrote papers with his wife. His wife would actually transcribe everything. There's some interesting recordings from his daughter of that process. And if you listen to the kinds of things he was telling his wife in terms of transcribing papers, it's like proto-LaTeX. They kind of developed it on their own. And so it's kind of interesting to hear that. The third person they hired was Professor Thelma Irene Arnett. She never got a PhD, never got any formal training in physics, had no physics degree. In fact, her bachelor's degree was in education. She had two master's degrees, one in Spanish and one in math. The interesting thing is she worked on the Manhattan Project at Oak Ridge. But she actually did like real technical work. So she got her training in nuclear physics actually at the nuclear reactor that was built at Oak Ridge during the bomb effort. And so actually her training in nuclear physics was far more extensive than the first two people they hired to build the lab here. She was here from 1960 to 1985, and she's completely forgotten. People don't really talk about her. People don't remember she was here. So part of my mission is to help remind people that she was an important part of the founding of the lab. And I have a whole talk about her work before she came to MSU, and the QR code is here. Even without any physics official credentials, she became a tenured physics professor at the physics department here. Very interesting story. Okay, so I'm going to go back to the dawn of nuclear physics. But to explain that, I want to provide some context for how that came about. Okay. In November 1895, so in sort of the late part of the 19th century, people had been doing extensive studies of electricity and magnetism. You had all of Faraday's experiments that led to Maxwell's equations. And then there was a whole series of experiments to validate Maxwell's equations. One of the key enabling technologies that was invented within sort of the last part of the 19th century was vacuum tubes. Okay, so you could actually see if electricity could go through a vacuum. So those were the initial studies. And then someone was, Röntgen was inspired to see, they realized that some of the electricity could be transferred outside the vacuum tube. And Röntgen had this idea, it's like, well, what if it produces light? And so he actually put some photographic film at the end on the outside of the vacuum tube. It was actually, it actually got exposed. And in fact, some of those X-rays were converted into optical light. So he could actually see it shimmering, because this was the discovery of X-rays. This is 1895. One of the amazing things about this is that, in the course of doing his, so this was December 1895. So within a few weeks later, he's studying this stuff and he's like, I wonder, like what kind of stuff does X-rays go through? So now what he did was he asked his wife to put her hand at the end of the thing, and they put the photographic film on the other side. And this is actually the first X-ray image ever taken. And that big blob right there is actually her wedding ring. I find this story amazing because if I do laser stuff, and if I want to try out some new laser stuff, there's no way in hell I'm going to go to my wife and she's going to say, yeah, sure, I'll stand right in front of your laser beam. So the standards of safety and things have changed quite a bit since the late 19th century. But X-rays are due to excitations and de-excitations in atoms, okay, of electrons in atoms. So this is in February 1896. So just like a few months later, Henri Becquerel asked the question, do you even need electricity to make X-rays? So he did similar experiments with photographic films, except without any source of electricity. And this is the entire paper where he showed that if you use certain types of chemicals, they actually cause photographic film to become exposed. And because there was no electricity involved, it had to be some other different process associated with the chemicals. You don't have to read the whole thing. These slides are posted. You can look at it later. But there's a comment in here by Mr. Neuenglowski. And he said, oh, if you buy certain types of paint and you expose it to sunlight, even in a dark room, days later, it's still glowing because of phosphorescence. Because Becquerel had said he'd gotten some exposed photographic film that was completely sealed. And this guy said, oh, no, you just messed up. It's some paint that had seen some sunlight, and that's what happened. So Becquerel actually did a series of experiments where he waited days after exposure to sunlight. He kept the whole experiment dark. And then he checked to see the photographic film, and it was still exposed. So that was a brand new thing. So shortly after that, it was found that radioactivity produces electricity. So this is the work, the collaborative work of Marie Curie and Pierre Curie. Pierre Curie actually was sort of an expert at measuring tiny electrical currents. This is using like 1880s, 1890s technology. They could measure currents at the level of a tenth of a pico. We try to do it in my lab right now with modern equipment, and it's super challenging. And the fact that they could do this back then pretty reliably is quite amazing. So it's a very sensitive instrument. If you look at this picture, this is Marie Curie, Pierre Curie, and you see this Y right here in the middle of the page, okay? So that's the instrument. This is the schematic. So this is the Y, okay? And the idea is that you put some radioactive sample in a ionization chamber. And when the radiation decay is emitted, the ions are collected up to this electrometer. And basically the way that you measure the current, there's no digital anything, right? Okay. So actually what they do is this mirror gets deflected as the plate underneath it gets charged up. And you have some light shining on the mirror, and there's a scale, and you look at the scale, and you see where the light spot is. So as the ions charge up the plate, the mirror gets deflected, the light gets deflected, and your spot goes in a different place. And so then what you have to do is by hand, you adjust the weight here, and you discharge the capacitor, and you keep track of how long it takes you and how much weight you released. And that's directly proportional to the current. And that tells you how much radioactivity there was. Okay, just super clever instrument. Requires tremendous amount of patience and creativity to use this kind of thing. And you can see if So you can see sort of the vast thing that Marie Curie is looking through. You can't quite see it, but in her left hand, there's a stop clock so she can measure the time. And her right hand, which is kind of obscured, she's adjusting the amount of weight that's compensating for the charge. I love this plot. This is from Rutherford's book in 1906 called Radioactive Transformations. This chart right here is all that was known about nuclear physics in 1906, okay? So interestingly, there were only two types of radiation, alpha and beta. They knew that the mass of the alpha had to be bigger than the beta. The velocity of the alpha was slow compared to the beta because, you know, the one line's longer than the other. And then they knew that the energy of the alpha was significantly more than the beta. And the main distinguishing feature of alphas and betas is you put it in a magnetic field and they bend in different directions. Okay, so this is a drawing directly from that diagram. So this is 1906. So things are starting to get clear. Another thing I wanted to mention is that Rutherford's first graduate student was a scientist named Harriet Brooks. This was when he first started studying radioactivity while he was in Canada. And that was his first appointment. He eventually moved to England later. Harriet Brooks was his first student. And what she did as her thesis work was to show that radium and uranium both produce helium and radon gas. Marie Curie's experiments actually showed that there was something more radioactive than uranium in the sample, and it was radium, and she could do quantitative measurements because of that instrument. So, you know, the ideas of nuclear physics were starting to be built in the early part of the 20th century. But for context, the idea that atoms even existed was still controversial. Okay, so we're talking about nuclear physics, and people aren't even convinced that atoms are real. One of Einstein's famous papers in 1905 was his mathematical description of Brownian motion. And then Perrin actually did experiments that validated those things. And the combination of those two things finally convinced most people that atoms are real. Okay, so while nuclear physics was still being uncovered in the early part of the 20th century, people were still arguing about atoms and their existence. This thing right here is from Wikipedia. The little black dots are the atoms in like a little dish of water, and that yellow thing is a grain of pollen. Those are the kinds of experiments Perrin did. This figure you're going to see a few more times, so I just kind of explain what it is. This is when sort of the modern ideas of how you do nuclear and particle physics experiments started to occur. And the idea is that you shoot one thing at another thing, okay? And then you look to see how much the beam is deflected. And generically, regardless of the math, you know, if you have a very diffuse object, you don't get a very big deflection, okay? And so if it's a finite size blobby object, the deflection is small, okay? And so this maps onto what was at that time called the Thomson model. On the other hand, if you have a hard point-like particle that's super dense, most of the time nothing happens, but occasionally the deflection is very significant, way more than you would expect from this model. And the idea was to try to do those kinds of experiments. So this is sort of the Rutherford model of an atom at the time. At that point, people knew that electrons existed, but atoms were neutral, and they believed atoms existed. So something positive had to be there. And the question was, what was the distribution? This is the actual data that the graduate students took in 1910-ish. Okay, so at that point, there was no accelerators, so the beam was actually a radioactive source. So the discovery of radioactivity allowed you to actually even create beams. There was a gold foil target. This is sort of what one looks like. You can buy these on eBay for 10 bucks. And then there was an eyepiece. So somebody had to look with their eye. Okay, and what were they looking for? If the alpha particle from the radium decay bounced off the gold foil, it would then occasionally go towards the eyepiece and would hit zinc selenide, which would give off a flash of light. So the experiment was some graduate student had to sit there, count the number of flashes of light as a function of angle. All right, I want you to look at the scale on the plot. What's the number right up here? How many flashes of light is that? 10 to the 5, 100,000. Listen, I can barely count to 10 without finding out. How they got to 100,000, I have no idea. Okay, and then they had to do it like a bunch of times at a bunch of different angles. Okay, and conceptually, you're going to see this plot. You've already seen a version of this plot at the presentations this week, and you'll see it a few more times in this presentation. But basically, the idea is that if you have a very hard point-like scattering, you get much more counts than and when you look at and theta can be mapped onto a resolution scale. In the language you're familiar with, theta is directly related to q squared. Okay, and the number of counts on the y-axis, in the language you might be familiar with, that's basically the cross section. Okay, and if it was fuzzy scattering, so a very diffuse finite sized object that didn't have a point-like character, the cross section would just drop off like that. And so this is sort of a modern view of the periodic table. This is sort of what a nuclear astrophysicist would look at. And basically the idea is that different chemical elements have different numbers of protons, but that's only half the story. The color coding here indicates where we think these chemical elements were formed. I want to point out that Big Bang and direct fusion, so hydrogen, helium, a little bit of lithium. So the whole rest of the periodic table had to be made somewhere else. And we believe that's inside of stars and in explosive stellar environments. And I'll come back to that a little bit later. Sadi was a student of Rutherford. And so what he started doing really systematic studies, and he measured the decay chains of these different isotopes. And by doing chemistry, he could distinguish which things were which. And what he found was in the decay chain, there would be like 40 steps before the thing becomes stable. But when he did the chemical analysis, there were only 10 different chemical elements. So this was very confusing to him. And so he talked to his neighbor, Margaret Todd, who is a doctor. And so he had the idea that like, well, maybe it's like somehow it's the same chemical element, but it just weighs differently. And so the name isotope actually came from her. And so that name stuck. And so that's the isotope part of the facility for rare isotope beams. Over the next 20 years, a lot of evidence accumulated that this was sort of the correct idea. And finally, the thing that really nailed it was the discovery of neutrons. So this is James, I messed this up. This is not Frederick Soddy. This is James Chadwick. This experiment is relatively simple. Again, there is no accelerator, so there was no beam. You have to use a radioactive source as the beam. So this is polonium, which would decay by alphas and hit a beryllium target. Again, there's a vacuum pump now. The vacuums they could achieve were sufficient for these kinds of experiments, so a lot of progress had been made. And then some neutral unknown radiation came out, and the original hypothesis is just gamma rays. What's interesting is at that time, people still used things like conservation of energy just like we do now. But if it didn't work out, there was always a question about whether conservation of energy was actually true on a microscopic scale. And this even came up when people were trying to think about explaining beta decay, and it led to the hypothesis of the neutrino. But the other idea was maybe energy and momentum is just not conserved on a microscopic scale. And so there was an open question. So he believed in the conservation of energy and said, well, then the stuff coming out actually has to be super high energy gamma rays, which doesn't make sense, or some heavy particle with nearly the same mass as a proton. And so in this experiment, the unknown radiation hits the paraffin wax, protons come out and they count the clicks. And so you can actually work backwards and say, yes, the things hitting the protons had to be something of roughly the same mass, but they're neutral. The idea of neutron had been around, but this was sort of the proof. There were other experiments done at Paris at the time by Marie Curie's daughter. They had the wrong interpretation, and they were sort of going down the blind alley, even though they did the experiment first. He did the first correct interpretation, and he conclusively showed it couldn't have been gamma rays. So all the elements are there now, so I can show you a nuclear scientist view of the periodic table. As I'll show you a little bit later, the people that work at FRIB are more than physicists. There's engineers, there are accelerator people, and there's a lot of chemists, and I'll try to explain where the chemistry comes from. But in this view, you have proton number going up, you have neutron number going to the right. Okay, so the periodic table is sort of going up, but then the neutron number, it gives you access to all the other isotopes. All the red boxes are the stable isotopes. Those are pretty well characterized. All the green boxes above, all the things above the black line is where you have more protons than neutrons. And all the turquoise boxes below is where you have more neutrons than protons. The thing that FRIB is going to enable is the study of all the stuff mostly down here. There'll be some stuff above, but a lot of the interesting stuff is on the neutron-rich side. In this picture, it looks like we know where the boundary is. We actually don't know the boundary. We only know the boundary up to like right about here, and that's it. Okay, so so that's maybe sort of in the magnesium region. So understanding that this is called the neutron drip line, kind of understanding where this is and comparing against theory is a big part of the game. Now, nuclear physics continue to evolve. Now, this is actually Hofstadter's data. So this is electron scattering data off of a proton. This was in the 1950s. And he was even described as sort of a modern version of the Rutherford experiment. In this case, you can see that the point-like scattering is the black line that's predicted, if assuming the protons were point-like particles. But actually what was measured was this red line, and it's slightly below the black line. And so that's an indication that you actually have some dense, that you have a very fuzzy, diffuse object. And there are other indications that protons were not point-like particles. For example, the magnetic moment of a proton has some weird number. It's not like the electron, which is just like a -2 or something. Okay. And again, this angle can be mapped onto what you might think of as Q squared. And Q squared, as you probably are very familiar with, defines sort of the resolution scale. So I actually made this, my background actually is electron scattering, polarized electron scattering. So a lot of the stuff that you guys are talking about is physics that's very near and dear to my heart. I just haven't thought about it in 15 years. But this is sort of a diagram I made where this is sort of the whole object. And if you adjust your focus and you look at different size features, the moon is kind of just a big blob that reflects light. Okay, but if you increase the resolution, you can see fine features like all the craters. And if you adjust the resolution and everywhere in between, you can kind of see different size scale features. That's what you can do by varying the angle in experiments. That's also what you can do by varying the energy of the scattered particle that you're looking at. Okay, experimentally, that's how you vary the resolution scale. So that seemed like the whole story. But then in the 60s at SLAC, they did these beautiful series of experiments where they went to much higher resolution scales. And the expectation very much was that they would just get this fuzzy scattering black line. If you actually read the original proposal, that's what they said. And they did not get that at all and took some time to figure out exactly what was going on. But you can see that in this case, what I'm plotting here is the number of counts measured divided by the number of counts expected for point-like scattering. For fuzzy scattering, it just drops, but for point-like scattering, as you increase and decrease the resolution scale, you sort of get the same answer. That's a real indication that some small, dense, point-like hard particle is inside protons. And so, this is my 9-year-old kid actually asked me this question. Proud father moment. And, they said, well, if I get that atoms have to be neutral, so you have pluses and minuses. But if the nucleus is all pluses and zeros, what holds it all together? Well, that's a good question. And I said, well, it's called the strong force, and there's a whole theory about it. And so so the modern picture is to talk about quarks and gluons. This is something you're all very familiar with. And I'll come back to whether this picture is even relevant if you're doing contemporary nuclear physics. I want to, okay. I know you're literally right here, right now. I know you all know you're not at the University of Michigan. I've given some versions of this talk before, and people go off and they go on LinkedIn. It's like, oh man, I had such an amazing week at the University of Michigan. FRIB's amazing. Ann Arbor's a beautiful city. Would definitely come back. Oh my God. All right, listen. Just so we're all on the same page, we are at Michigan State University. Our colors are green and white. We are very bad at American football, but for the purposes of why you're here, that doesn't matter. We have FRIB, and we do a lot of nuclear science. The other place, very good at American football, at least a couple of years ago, and doesn't have an FRIB. Okay. So this is the modern version of the FRIB logo. And the logo kind of highlights the science that's done at the facility. The first proposal to build something like this was in 1991. And it took 10 years for that idea to gain traction. It morphed quite a few times. And then it didn't become a community priority until the early 2000s. And then there was a process with like a National Academy of Studies saying, yes, we agree, if you build this thing, it could be very impactful for nuclear science and many other things in general. And the contract to build this facility was awarded to MSU in about 2008. And this was finished construction in late 2021, and we started producing beams at May 22. Okay. We have just reached 1/40th of our design power, so it's a slow ramp up. At the power that's already been achieved, it is the most intense rare isotope accelerator facility in the world already. Okay. And we're going to go 40 times higher than where we are now in the next 5 years. The science generally is nuclear structure, nuclear astrophysics, societal applications, and fundamental symmetries. I'm going to give you sort of a bird's eye view with a few examples of what those things are. And I've tried to pick some examples that are kind of hot off the presses. Well, the nuclear structure example for that was actually an experiment done here, and it was published last fall. It's hard. Okay, so one thing I want to convey is we are not making any new elements. No new elements here. No super heavies, nothing like that. The basic structure of the facility is that we can accelerate nuclei as heavy as uranium-238. We smash it against a carbon target, and that makes a whole bunch of stuff lighter than uranium. In a few cases, slightly heavier than uranium, but generally below. Okay, so we're not making new elements, but what we are doing is providing access to lots of different isotopes on that chart of nuclides in quantities that are sometimes 1,000 to 1,000,000 times more than any other place on Earth, which allows you to actually do experiments that wouldn't have been feasible before. That's sort of the idea. Okay, so this is from a paper published in 2012. This dark blue band are all the isotopes that had been created and studied minimally up to about 2012. The light blue band are theoretical calculations that looked at the stability of all the different isotopes and whether they would be bound long enough for you to do any kind of interesting experiments, and they set some metric and thresholds for what that would be. And so if you look at this, you'll see that actually we've barely scratched the surface of nuclear physics, right? This is only about 1/3 of the isotopes that we think could be studied have even been produced and studied in practical quantities. I was trying to think how to convey that. And so you can make an analogy to the periodic table. Okay, periodic table has something like 118 elements. And if you ask it, what year did they had discovered 1/3 of the chemical elements? That was 1800. Okay, so if you compare nuclear physics to chemistry, we are now in nuclear physics where chemistry was in 1800. And there was a huge explosion in chemistry in the subsequent 150 years. Because of FRIB, that 150-year discovery timescale is going to be contracted down to the next 20 years because of this facility. All right, so there's going to be a whole bunch of stuff we're going to learn and a lot of surprises. I'm going to give you a little flavor of what some of those things have already started to look like. Okay, and then this green band is what we think FRIB can produce. So this was estimated almost 13 years ago. We now have some experience with the beam. I think the area is the same, except some of these peaks are taller and some unfortunately are shorter. Now that we have a little bit more experience with what the beam looks like. Okay. There are a variety of ways. Well, actually, there's really just two ways you can make a new isotope. In the ISOL technique, this is the kind of thing that's at CERN right now at their Isolde facility. What they do is they accelerate a proton beam into a big block of uranium, okay? And they just irradiate the crap out of it for a very long time. And that makes everything, okay, inside this box, but you got to get the stuff out of the box. So what you do is you cook the box to a very high temperature. And because of the chemistry, some stuff comes out and some stuff doesn't. And the stuff that comes out, ISOL is the best technique. It is amazing. You get really high rates. There's a lot of really beautiful and important experiments you could do at Isolde. They're sort of the world leaders at it. Triumph, which is a nuclear physics facility in Canada, is also building their own version of that. And that's going to be very important to the nuclear science community. But it all relies on the chemistry of the thing that you want being good enough that you can cook it so it comes out. A lot of stuff doesn't. Okay. So the other way to do this is something called in-flight separation. So there you reverse the thing. All right. The uranium is not the target anymore. It's the beam. Okay. And in this case, the target is essentially, it's carbon, it's graphite just for its thermal properties. It's a lot of beam power we're dumping on this thing. You don't want it to melt. So you kind of flip the heavy thing with the light thing in terms of beam and target. And then you make a whole bunch of stuff and it splashes all over the place, but it's mostly forward scattering. Okay. And then you can separate out the secondary beam of interest and send it down to where your experiment is. And then all the other stuff that's produced, the other, I think will be every collision or every beam with uranium-238 will produce something like 8,000 of the 10,000 isotopes we think are possible all the time. We only pick one, and the other 7,999 isotopes are just deflected away. We actually don't throw that away, and I'll talk about that in a second. But then that secondary beam is very fast, and for some experiments you want that because of time dilation. You want a short-lived isotope to be moving very fast, so it lives long enough in your reference frame to study it. And you basically build a bunch of gamma ray detectors around the beam line to watch it decay. All right, so that's one type of experiment, and I'll show you results of an experiment like that. In other cases, you actually want to slow the beam down to a complete stop. So there, what you do is you dump the secondary beam into a bucket of cold helium gas, and there's some gentle electric fields, and the whole bucket actually is more like a funnel, and it gently completely stops the beam, guides the beam out at very low energies like EV, okay? And then you accelerate it back up to whatever energy is necessary for your experiment. And so that's kind of sort of shown here. There's sort of the secondary path. Those kinds of measurements, the kinds of measurements that require a slow stop beam are mass measurements. The mass measurement stuff is amazing. They can measure the mass of a single nucleus. If with the intent until it decays. So then you need to load it with another one. But the sensitivity is such that you can do it one nucleus at a time. The reason you need something like FRIB is that the thing decays away quickly. You need to load the trap again with another single ion so you can accumulate statistics. And you can do mass measurements out to 9 digits. And this kind of information has a lot of applications between nuclear physics and nuclear astrophysics. You can also do laser spectroscopy if you neutralize the thing. And that tells you something about the size and shape of nuclei. So I want to focus a little bit on sort of this in-flight production. This is sort of the cartoon picture. This stuff mostly is forward scattering because most of the momentum is in the forward direction because of conservation of momentum. The key thing and the whole reason MSU won the bid to build FRIB is that once it was decided that FRIB had to be an in-flight facility as opposed to an ISOL facility, the reason for this choice is you get access to all the isotopes. The chemistry doesn't matter. Everything is produced, and as long as you put in the right electric and magnetic fields to separate out the thing that you want, you have access to all the other things. If you can make it with ISOL, go to CERN. That's the best place to do it. If they can't do it, come to us. Okay. Our competitive advantage for winning the bid, the other team that bid on building FRIB was Argonne National Lab. Our competitive advantage is all this stuff right here. Let me try to explain what that is. Before we were the facility for rare isotope beams, we were the National Superconducting Cyclotron Lab. We actually built the world's first superconducting cyclotron, and that basic design is what's used in every medical isotope producing cyclotron across the world. That design came from MSU. This is the original one, K500. This is the second one we built, which is bigger. Roughly speaking, you can take the ratios of those numbers, and that tells you something about how much more better it is. Okay, that's fine. I won't tell you what the metric is. Okay, and so the idea here, would you take something like krypton 86, and you want to make nickel 78. Okay, so nickel 78 is lighter, but has more neutrons. Okay, so you send it through the K500, you accelerate it up to the K1200, that accelerates it up even more. And then there's a little thing here called the production target. That's where the smashing happens and all the stuff is produced. And this is everything that's produced. So this is neutron number, this is proton number. The nickel 78, the thing you care about is this tiny orange dot right on the edge. Okay, but you've produced all this other stuff. Okay, so what you do is through a series of ion optics and dipole magnets, you can separate out different fractions of this phase space. So after the first filtration step, you actually got rid of all the stables. There's just the radioactive neutron-rich stuff. So you take advantage of the fact that the mass, the charge to mass of your the charge separately from the mass, separately from the charge to mass ratio, all gives nickel 78 a unique properties, and you take advantage of all those three things. And so this beamline here, we built, this is the best one in the world. It's called the A1900. That was our competitive advantage. And we said, this is the thing you got to get right. Let us build FRIB. DOE bought it. Okay. So then after all the steps, this is what's left over. Nickel 78 plus a few extra things. Okay. So this filtration process is very important. And that's the thing that we're particularly good at. And so the idea for FRIB and the pitch that we made was, well, we already have this thing and it works super good. So we're just going to replace the source, which was 2 cyclotrons, with a high power linear accelerator. Okay. So this is the building over. You're going to get a tour of this place. Okay. You're going to come in right here. You're going to walk down this main hallway, and you'll get to see a lot of the experimental areas. where the beams at different energies are used for different experiments, laser spectroscopy, ion trapping for mass measurements, nuclear reactions, gamma ray spectroscopy, all that kind of stuff is sort of all in these regions up here. The cyclotrons are still there. It turns out that this cyclotron is still useful. The electronics industry are building a lot of like electronic circuit boards that are very dense, that have a lot of electrical components. If you've ever seen a circuit board, it's sort of a two-dimensional thing. The kinds of electronics people are building now are sort of three-dimensional things. And there are a lot more circuit elements. And the concern is that cosmic rays might come in and knock out one of these circuit elements. And the question is, how much of that can happen before your whole device fails? And so you actually need the ability to put radiation into a thing at different depths with different amounts of energy, so you can mimic all the different kinds of cosmic rays, especially for stuff you send out into space. And so the industry that cares about that, we call them the chip testing industry. They need a place where they can just put their stuff and see how much damage occurs. And so this was always a little side project. And then they said, hey, we have so many more, like our industry is growing, we need a lot more testing. Is there anything you could do? And we said, oh, well, you could use one of our old cyclotrons. We're going to use them anymore, but it's super expensive to fix. Like, it's old and kind of degraded. It needs a lot of upgrades. It's going to be too expensive. And like, well, how much, just spitballing, how much does it cost? And we were like, oh man, it's going to cost like $20 million. They wrote them the check that day. And so if you go out there and you see the building being built, that's the chip testing facility that's going to interface with this cyclotron. And they're refurbishing it right now. It's just different industries have different scales. So just think about that in terms of career stuff. Okay. So that's what's happening there. All of this is built and it's in operation right now. The thing that we're doing is we've defined a bunch of science elements that you can do with different beam intensities. Because no one's even gotten close to within 2 orders of magnitude of the beam intensities we're going to produce. We actually don't know what some of the hazards are, so we're slowly ramping it up to make sure we don't mess anything up. And so there's several epochs. We'll be at full power in about 5 or 6 years. And we have plans for an upgrade. I don't know if you see here this purple thing that says Linac segment 3. There's a whole empty space there. We planned for the future knowing that we were going to ask for more accelerator elements so we can get even higher beam intensities. And so that's in the works now. We know how to build it. It's straightforward. We have the expertise, just don't have the money. And so I think we're going to have to wait maybe a few extra years more than we originally thought. Okay. But the idea is to add more stuff here. So the life cycle of this facility, we're just at the beginning, and I think we got a good 30 years going forward. Okay, so now let me talk about some science highlights of what you can do with these beams. This is a picture of Maria Gerpert-Mayer when she was maybe 10-ish years old. I love this picture because for Halloween, she dressed up as Batgirl. This was like in the 1930s. I don't know if Batgirl was a thing. She was way ahead of her time for lots of different reasons. One of the things, so many interesting stories about her. She was not trained as a nuclear physicist. She was actually a theoretical quantum chemist. And she was a professor at the University of Chicago. And because her husband was also a professor there, and due to nepotism rules, she was not paid a single penny by the University of Chicago. They said she could have an office. They said she could advise graduate students. They said she could teach quantum mechanics to all the students. They said she could publish papers. She could do all the things. She wouldn't get, and teach classes, and not get paid a single penny. Now, her and her husband didn't really care about money, but they had kind of an extravagant lifestyle. They loved throwing parties. They were very social people. They couldn't cook, so they had to hire caterers to like come do, cater all their parties. And so at some point she got frustrated with not getting paid for doing really amazing science. And so her former graduate student ended up being head of the nuclear theory group at Argonne National Lab. And he said, hey, I can get you a job. She's like, oh, that's great. I do like jobs. Paid, right? And he's like, yeah, absolutely. And she's like, oh, great. Oh, man, that's awesome. Okay, good. So she goes out to Argonne and he's like, oh, but there's a catch. She said, well, what's the catch? It's like, we actually don't give a shit about theoretical quantum chemistry. You got to do nuclear physics. She's like, but I don't do nuclear physics. He's like, well, we will give you money. And she's like, okay, fine. And so Argonne at the time, the theory group was new, but the experimental group was amazing. And they were collecting all this data and none of it made sense. So every day she was talking with the experimentalists, looking at their data before it was published and seeing all these interesting patterns. Okay, so if you've heard of the concept of magic numbers, that's what these lines are on this chart of nuclides. Okay, those are particularly stable combinations of protons and neutrons. And so that the observation was there, and they're called magic numbers because that's a derogatory term. Some scientists thought, okay, well, sure, they're unusually stable and they happen to come at these numbers, but that's just a coincidence. They're just quote unquote magic numbers. But she really bought into it. And because she had done theoretical quantum chemistry, she was very familiar with atomic structure. And she took those ideas and applied them to nuclear physics, substituting electrons for protons and neutrons, and realizing that the spin-orbit coupling between protons and neutrons is way bigger than electrons and nuclei and atoms. It can explain the gross features of this chart of nuclides. Okay, and that actually won her the Nobel Prize in 1963. She did get paid by Argonne to do her Nobel Prize winning work, but University of Chicago didn't pay her a single penny. The best part of this story, actually, there's so many good parts. So eventually she got tired of the University of Chicago and she left. She went to UC San Diego, where they offered her a paid professorship. I actually gave a version of this talk in the University of Chicago colloquium room. And guess what? Who is it's named after? It's the Maria Gerbert Mayer conference room. And I told this story. I have never been invited back to University of Chicago. Okay, now, so nuclear shell model is amazing. Okay, but it is just a framework. It's just scaffolding. It doesn't do all the details. Okay, so I want to put it in language that maybe you can appreciate. Okay, hopefully you guys have heard of the constituent quark model. Yeah, okay, that's fine. As long as I'm talking to you then. Okay, good. All right. The constituent quark model also did a pretty good job explaining like the spins and things of hadrons. Man, but you cannot do any PDF stuff with the constituent quark model, right? It just tells you nothing about that. Okay. And so the nuclear shell model for nuclei is an analogy to constituent quark model of hadrons. It gets some stuff right, but there's so much of the picture that's missing. And the idea of FRIB is to fill in those gaps. So I'll give you two things that the nuclear shell model gets wrong. There are places in the chart of the nuclides where you think you're supposed to have magic numbers, and they are not magic, right? So that whole textbook story you might have learned when you took Intro to Modern Physics about, oh, shell model explains everything, Nobel Prize is done, nuclear physics dead field, wrong. The idea that like some numbers where you think are magic are not magic, that was, a discovery made in the last 15 years. And so there's a real big effort to try and understand what's going on. Another thing is, if you use the shell model, normally you can predict the ground state spin and parity of the nucleus. You can predict its ground state properties, okay? And if you do that in certain parts of the chart of nuclides, you get completely the wrong answer, okay? And one place is near chromium-62. So this is a beam that was produced at FRIB in large enough quantities to study for the first time. This says detector, but actually the detector is something called gratina. It is a 4 pi detector. All right, big sphere on the beam line, looks at gamma rays at every angles. Very expensive. Actually, the most expensive part of gratina is not the detectors, it's all the iron to make the frame. Weird. Okay, so this was published just this past fall. And so, there's these two shapes for the nucleus that gives you different sets of energy levels. And actually you see both. Okay, so you see both sets of energy levels from experiment. That means as you go up the energy level, the shape of the nucleus you need to describe why it has an energy level just bounces around and changes. That's called shape coexistence. That's also, that idea was hypothesized in the 70s. It's only really being studied now. Okay. So, different degrees of freedom are used at different energy scales to predict nuclear properties. I read this quote when I was a graduate student by a nuclear physicist. His name was Herb Anderson. They were at some conference looking at celebrating the 35 years of electron scattering. And it said, this was 1987. And Herb Anderson said, "We have been doing nuclear physics for 50 years without quarks. Why do we need them now?" My understanding is you can ask that question today and it would still be relevant. And this is a deeply interesting and fascinating question. I encourage you to think about it. There's lots of interesting hints that nuclear physics does play a role, even when you talk about things in terms of quark degrees of freedom. Some buzzwords are like short-range correlations and the EMC effect, okay? But this is, in terms of a scientific question, I think this is one of the most interesting ones. I just don't have the skill set to answer this one, so I just kind of hope somebody else does it. Okay. Quick E&M review. Josh knows I used to teach E&M to the graduate students. Opposite tracks, like charges repel. All right. So why that's important is that if you think, how do you build up a nucleus? Well, you need two positively charged things to come close enough to fuse, but they're positively charged, and that repulsion is so strong they actually don't come close enough to fuse. Okay. And so the idea is that you actually need neutrons to sneak in and be captured by the nucleus so you can build a bigger nucleus, and eventually becomes unstable beta decays. A neutron turns into a proton, bam, new element. Okay. And so how that understanding that process was needed, and there are different ways to do that, was known in the 50s. Margaret Burbidge was a giant in nuclear physics. She's actually an astronomer by training, observational astronomer, actually. And the realization with her, her husband, and a couple of other nuclear scientists was that all of this stuff has to happen in stars. And they generally got the idea, and this is a drawing from their famous paper from 1954. It was a review article. It was not a review article. It was all new physics. Somehow they got it published in Reviews of Modern Physics. But the idea is that there are different kinds of processes. You can have neutrons captured very slowly relative to how fast something beta decays, or neutrons can be captured very quickly in a millisecond in a very violent stellar environment, way faster than the beta decay timescale. And so FRIB is actually going to produce a lot of these R process elements. And this R process really became super exciting in the last 10 years because LIGO actually made an observation of a neutron star binary neutron star merger. And there was even an electromagnetic signal, and there was even hints of an optical signal showing that some R process elements were being made. This electrified the community. Very good for us from a PR point of view because we are riding on the LIGO coattails. Say, oh yeah, we're doing a neutron star merger side. I mean, that was always true. It's just, it would help that they actually saw one. Another thing, okay, so I said we separate one part of the beam and throw the rest away. We actually don't throw the rest away. All the rest gets dumped into a bucket of water that becomes super radioactive. And that water flows to a lead-lined chemistry box where we use robot arms to take all the other stuff out using radiochemistry. It's very cool. These are some of the people that do it. So now, if those isotopes live long enough, you can actually use them for other things like plant biology, studying root systems as radioactive tracers, treating cancer, fundamental symmetries. That's the thing I do. And when I was hired, it was just a dream. They were still having workshops trying to convince DOE to give us the money. This is real now. This is what the lead-lined chemistry box looks like. This is actually lead glass, okay, and it's very thick, like a foot thick, because you got to block the radiation. The water cycles through in here in a lead-lined stainless steel tube, and it pops up inside. These are all manipulator arms. They're not really robot arms. Somebody actually has to hold onto these handles and manipulate the radioactive beakers and stuff. And sometimes you can't see, so there's a mirror inside. You got to look at the mirror reflection to make sure you don't drop the radioactive stuff. There are highly trained people who can do that, not me. But this is real. This actually exists. I hope you can see this, but if not, here's a picture. Okay. The big application, super exciting one, is to build heat-seeking missiles for cancer cells. Okay, this idea has been around as soon as radiation was used to treat cancer. But in the old days, you just put in somebody and the radiation killed everything, including the healthy cells. And that's why people undergoing cancer therapy or radiation therapy, they lose their hair, they lose weight, they look sickly. It's because radiation is also killing the good stuff. Okay, so it was known that was bad, but it took a long time to figure out how do you get something that decays that only selectively kills the cancer cells. And so the idea is something called targeted alpha therapy. Alphas don't go very far. They deposit their energy very near from where they're emitted. Okay, so if you can put an alpha emitter near a cancer cell, it just kills the cancer cells. But figuring out how to do that requires chemistry, and you got to find something with a reasonable half-life. You don't want the thing in there killing cells after the cancer's gone. Okay, and you need something that decays with as many alphas as possible, so you get many punches. Actinium-225 is one example. They finally, so what chemical attaches to cancer cells? I don't know. It's called DOTATOC. It's a magical chemistry thing that also attaches to the actinium. So now you put that thing, it goes to the cancer cells, the actinium kills the cancer cells. That's great. Here's an example of a patient that was given like a month to live. The experimental treatment back like 10 years ago. All these black dots are really bad cancer, and after 2 treatments, all good. I don't know what happened to them, but anyway, this paper was published in 2018. This is just one example, and it only treats certain kinds of cancer. FRIB is going to produce lots of isotopes that gives us a lot more options to see what else is out there. And we have 4 radiochemists just waiting to get their hands on this stuff to do this kind of work. Last thing I will say is that nuclei are a unique laboratory to study all the fundamental forces, even new ones. Parity violation was initially observed and discovered in the beta decay of cobalt-60 by Madame Wu, my all-time favorite science superhero. So that was for parity violation. We think time reversal violation, in particular CP violation, is needed to explain why there's more matter than antimatter in the visible universe. We have a number for that based on this anisotropy in the cosmic microwave background radiation. That's all these dots. You study the size of these dots and the distribution of these dots and use some complicated general relativity, which I don't understand. You can actually calculate how much more matter than antimatter there is in the visible universe. It's not 0, but it's a tiny number, and you need CP violation to explain that. So theta QCD could be a source of CP violation, but also new physics. So this is where probably you guys work, somewhere up here, maybe in the middle. I'm right at the very bottom in the garbage where we look for low energy observables of CP violation. And so we use a lot of laser techniques to study weird systems that have unusual sensitivity to CP violation. Those kinds of experiments are called electric dipole moment experiments. And what I'll say is that the thing we actually measure if it's a nucleus, the CP violating observable, is something called the nuclear shift moment. We'll go through this real quick. I will just say that the nuclear shift moment that you observe in the lab has 3 components. This blue part is the new physics we're trying to measure. Okay, that's the same for everything. Then there's some matrix element that describes how asymmetrically deformed the nucleus is. And a pear-shaped nucleus is super deformed, big numerator. And then you look at the ground state of the first excited nuclear energy level above it. If it has the same spin but opposite parity, then it goes into this sum. And if you have a small denominator, this is just first order perturbation theory and quantum mechanics, small denominator, large numerator, you get a huge enhancement in terms of the observability of this new physics. And there are pear-shaped nuclei. Things like radium-225 are a great example. I've been working on one experiment for almost 15 years now. But the future is to do these experiments with molecules. And the molecules have a very complicated quantum mechanical structure that allows you to control for false effects and measure them separately than the CP violating observable. So you can reject false effects. Molecules actually have a large internal electric field that amplifies the effect of new physics. So if you put this all together and you take what's been achieved by the atomic physics, laser physics community and stable molecules and say, can we do the same with radioactive molecules? For certain types of new physics, we have a physics reach 1,000 times the energy reach of LHC. That's like in 30 years. Okay. And there are many ways to enhance even those estimates. The key thing is, in practice, to get these isotopes in practical quantities, you need to be at a place constantly making them. FRIB is that place. Thanks so much for your time. I appreciate it.
Do we have time for questions? And so you won't be able to clear on this evening, so I encourage you to ask about that.
Well, I would be, except my wife and I are going to see Book of Mormon, so I'm not going to be hanging out with you guys. Yeah.
Yeah.
Oh, yes, please.
Can you go to slide number
22, okay.
Then we plot here. The plot here for the estimated possibles, it looks like
This right here, yeah.
yes. So if I look at each of the bins, it looks like there's a bias. Like in alternate bins, there's a bias of around 10 isotopes. So,
Oh, yeah, you're talking about sort of like, why is there an alternating pattern? Yeah, this is completely related to the fact that if you have, let's see, what is a simple, okay, let me do it this way. If you have an even number of protons and an even number of neutrons, that's way more stable. One way you can, and actually, a total, if there are an odd number of protons, even, even protons, even neutrons, most stable. Odd protons, even neutrons, or vice versa, less stable. Odd, least stable. Part of the reason is related to the fact that you have Pauli's exclusion principle. And if you have the two spins anti-aligned, that helps a lot for the protons. Yeah. Oh, and so if you look across, I think these actually are, forget how wide these bins are, but that's what's being reflected. And in fact, this pattern, if you add one proton or one neutron, you go across and you're doing scans of different isotopes, whatever observable, you will always see this staggering pattern. And it's directly related to this idea that even numbers of stuff is always better than odd numbers of stuff, because you get filled shells or partially filled shells. It's a lot like the Aufbau principle in building up different electronic shells. So here the nuclear shell model works well. Dan.
well, here in system involves quarks interacting with the weak interaction. These violations in nuclei, even in all of them, do they also involve that same interaction of force fields with W fields?
Yes and no. So that interaction you're talking about, the CP violation that's encapsulated in the CKM matrix that you can use to describe kaon decay, that is always occurring in nuclei. And the observable that you would see as a result of that CP violation, if it's an atom, we call that an electric dipole moment. If it's a molecule, we just say it's a CP violating energy shift in some molecular levels. In atoms, because I can say it more easily in those units, you can actually calculate how big of an EDM you expect from standard model CP violation from the CKM matrix. And that number is something like 5 orders of magnitude smaller than the current best experimental limits. And the idea is that if you have some sort of quark coupling to exotic new physics, it also violates CP. The only way that's interesting is if that level of CP violation is significantly more than the standard model. That means if we see something as we increase the sensitivity of our experiments to the standard model limit, then that's a very strong hint that it's actually new physics and not quote unquote standard model background. The interesting thing about these molecule experiments that are being planned and designed right now, if you use a pear-shaped nucleus, within our lifetime, so within 30 years, using numbers that have already been demonstrated for stable molecules, we will be able to see standard model CP violations, which means if there's anything to discover within that window, we should be able to see something. Yes, I appreciate that comment. So oftentimes funding agents will say, well, what happens if you don't see anything? I'm like, well, actually, that's actually more interesting, I think, because, whenever I talk to people who do sort of like extensions to the standard model, it is hard to do that without having more sources of CP violation. And in fact, you kind of want that to explain the baryon asymmetry of the universe. So the story fits together really well. And it's, okay, now let me talk a little bit about the history. For as long as people have been doing these EDM experiments in 1950, the papers always say, well, we didn't see anything, but there's a paper that was just published that says if we improve our experimental sensitivity by an order of magnitude, we will see or rule out this thing. And then they don't see anything, and then they write another paper saying, well, our parameters were wrong, we fit to some other stuff. If you do an experiment that's 10 times better than what you've currently achieved, you will definitely see something. That's been the whole story since, I would say, at least 1970. And I actually love that experimentalists and theorists can work together to keep getting funding to do these experiments and calculations. Yeah.
Actually, like the fact that they brought up this connection tied to UCD and nuclear physics, right? And one question that I was preparing for the discussion was the statistics that we investing in quarks, carbon quarks, quantum model, which is UCD, and that's something that's we'll discuss. But if you have other questions for the discussion,
the one you're describing in my mind is sort of like if you're a nuclear physics person, it's like an analogy you can use to talk about what these different models mean in that sector. What's the analogous thing in terms of understanding nuclear physics? And there is, this is if you go to any nuclear theory talk, you're going to see this diagram, and somebody's going to point and say, I'm doing calculations here, or I'm doing calculations there. And if you kind of look at this, you start with quarks, you get protons, then you forget about any quarks, it's protons, neutrons, and pions, and it's the pion that's being exchanged. Forget about quarks and gluons altogether. It's all hidden in pions, right? And then you have clumps of protons and neutrons, and then you start losing their individual character. And then you kind of get this thing, which is basically just a modern version of the liquid drop model, right? It's just a smeared out blob. One of the interesting questions in nuclear physics is how do you use renormalization group methods to connect all these things? For the stuff you guys worry about, it's sort of like the question of how, it's a little bit more firm because you have DGLAP, but you know how to kind of do some of the evolution for different resolution scales, but it's always the same degrees of freedom. For us, we have lots of different degrees of freedom, and how you do that, integrating out different degrees of freedom is actually not clear. And so my question maybe for you guys to think about is, one way if I'm a dumb experimentalist, so when I learned about quantum field theory and renormalization, finally somebody said, oh, you're just averaging stuff out and blurring the image. I'm like, okay, great. So if you do that, like, does any quark stuff have any relevance to anything that happens at FRIB? And I'm deeply interested in that question. Yeah, Dan.
Low energy. Replace, you can approximate QCD by an effective field.
Yeah, chiral, yeah, like things like chiral effect, yeah. Yeah.
So it's an energy scale problem. finding energy that's small enough that you could just replace UCD as an approximation by an effective field theory of photons, big delta resonances.
Right. No, and so there, I mean, there are people who do exactly that, and they need low energy nuclear reaction experiments to measure like the low energy constants that you need to define your effective field theory. And I just, so, you know, part of the reason the CP violation stuff is kind of interesting is that arises because a quark is doing something weird. And it shows up as in a very low energy observable that's CP violating. So there I can kind of see the connection to a quark directly. Other nuclear structure stuff, I don't know. And you can do this sort of systematic, you know, power counting stuff and build effective field theories. You know, my heart, you know, I grew up doing electron scattering at JLab, and we measured things like this. And so, polarization dependent PDFs. And so I always want to find some connection, but, you know, if you think about this sort of framework of renormalization, all that stuff gets averaged away and it kind of is not relevant. And so this quote has really stuck with me for a long time.
Do we have one more question?
Yeah. So, my question is about the pair shape. So, first of all, what isotope actually takes on the pair shape? And then, also, how do you explain that it takes on the shape? It's kind of hard to think about normally when you have like asymmetries. Normally, when you perform nucleus, it's like some symmetric components, but
Right.
But then this is like, okay, it's symmetric in one axis, but you see something like this normally, it's like an alpha cluster creating a nodule on the nucleus or something, but this doesn't look like that. How do you explain?
Yeah. Okay. So this is right. This is a great question. Okay. So this picture right here, this is in the body frame of the nucleus. The nucleus is actually rotating and spinning around and all sorts of stuff. Okay. So if you're in the lab frame and this is not the picture you see. In the lab frame, you see this rotating around so much and any random axes that this averages out. And you actually don't see pear-shaped deformation in the lab frame. Okay. But in the body frame, it's there. So if you're standing on this thing and you're rotating with it, you will see this deformation. Okay. And in fact, if there's no CP violation, that averaging results in exactly 0 deformation in the lab frame. Unless there's new physics that causes the deformation to rotate about a preferred axis so that the deformation remains in the lab frame after averaging. And you can see, and the way you see that in an experiment is you measure something called the electric dipole moment, for example, or a nuclear shift moment. That's the signature CP violation. So if it's just strong interaction, theta Q rotating around, you actually don't see this deformation in the lab frame.
That's thanks to again. So
All right, thank you.
we talked about ranking the start at 10:45 then.